Yes, I'm Carlos Arguelles from National Research Council of from Argentina, CONICET, which is the National Research Council of Science and Technology, and also from La Plata National University, also in Argentina, and also in collaboration with ICRANET Institute in Italy. So today we'll present a new channel for supermassive black hole formation, and the work is I will present the results of this paper, which has been published recently, but also I will show results from former works in the last 5 years, which are the ones that you can read below. I have these results have been done in collaboration with the people you see here. First people from Ruffini, Rueda, Crut from ICRANET, then in collaboration for people with other institutions, including Argentina, some PhD students, and recently also collaborating with Pierre-Henri Chavani, one of the world experts on cell gravitating systems. Okay, so the main idea of this talk is based on the assumption that we have a neutral massive fermion, which is present after inflationary epoch, and we will be rather agnostic about the decoupling physics of the fermion, which will just assume that it exists a spin 1/2 neutral massive fermion, which decouple in a given regime, which could be either freeze out or freeze in. It will depend on the microscopic model you want to choose, and this particle will become a relic, which after you study the evolution of the density perturbation, you will start to form the pristine halos that start to form the cosmic web and then the galaxies as we know. So the challenge will be to form halos out of these fermions, which will start to enter in the nonlinear regime, in the cell gravity regime, and this will be the main challenge of this talk. So you may wonder what this has to do with supermassive black holes, and this is the thing that it may be a bit surprising, but interestingly will come out soon. So the fact that we are dealing with elementary particles, cell gravitating fermions, we cannot work under n-body simulations. But so therefore we will use a statistical mechanic approach for this analysis. So we start with the Blasov-Poisson equation, with F is the mass density of particles in phase space, which is coupled to gravity here. And so this equation, interestingly, can be the phase space density can be deconvolved or expanded in a coarse-grained phase space density plus fine-grained fluctuations. And then by taking local average of this equation, you can end up with a convection diffusion equation where the left-hand side resembles the Blasov equation for the coarse-grained distribution function F, and in the right-hand side, you have the diffusion current. This approach has been developed by Chavani in the 1998, and the fact that this equation is very difficult to solve because consider that the phase space density depends not only in position, velocity, but also in time. So you have all these particles that start to collapse under cell gravity and go very rapid and violent fluctuations. So a way to solve this is to impose a maximum entropy production principle, and which leads to a possibility to write this equation into a generalized Landau equation, which I will not enter in the details here, but this equation can be solved analytically and show that the most likely coarse-grained phase space density out of this solution of this equation is of Fermi-Dirac type, which is probably some of you recall that is a generalization of Linden-Bell distribution function theory of violent relaxation. But in this case, it accounts for escape of particle effects, because for particles energy above m energies, this parameter E sub m, there are no more particles in the distribution, and therefore you have this cut of distribution. So this, if the particles you want to study are fermions, then the maximum accessible value of the phase space density is, as you know, given by this formula, proportional to the m to the fourth divided by h cubed. So once we have this most likely coarse-grained phase space density and relaxation from this theory, you can try to build the halos in equilibrium solutions for self-gravitating fermions. And so the first thing is that fermions under self-gravity do admit a perfect fluid approximation. This was shown in the pioneering paper decades ago by Ruffini and Bonasola. And then it is possible to solve the Einstein equilibrium equation for a Fermi gas at finite temperature. So you start with the equation of a state, which is parametric equation of a state. It's a bit complicated because it's not polytropic. So you have, it's an integral of the coarse-grained phase space density F, which I showed you in the slide before. And the energy we will, the energy of the particles will maintain the most general expression, which is relativistic energy. But this depending on the momentum, this can achieve relativistic regimes or not. It depending on the situation. And so this problem has 4 free parameters, which is the particle mass, the effective temperature, which is beta normalized with mc squared, the degeneracy parameter, which is chemical potential divided by kappa T, and the cutoff energy value. And so the system of equation is the mass equation, the traditional mass equation, then the Tolman-Oppenheimer-Volkoff equation. These two are the Einstein, two relevant Einstein equation in spherical symmetry. And then Klein and Tolman, which is zero and first law of thermodynamics in general relativity. These 4 equations, interestingly, come out naturally by making a first order variation of global entropy of the problem, which I will not show here, but they can be naturally a solution when you make this first order variation. Therefore, this 4 equation has to be considered all together. And then we have also the energy conservation along geodesics, which is written in this dimensionless manner. So we have this coupled system of equations, and it is a boundary condition problem, which you have to solve at the center of the configuration. And so interestingly, the most general solution of this system is it implies this density distribution that you can see here in continuous line. This solution has been solved for specific outer boundary conditions typical of a spiral halo of these values here at the 1 halo scale length of this model, which is at the second maximum of the rotation curve, so at the so-called halo maximum of the rotation curve. And interestingly, this solution, as you can see, have 2 regimes in the same solution. So from outer to inner, they are in the outer part, they are governed by thermal pressure. And then towards because this profile resembles the Boltzmannian profile with a cutoff, if you want. And towards the center, due to the degeneracy is a monotonic function in radius, so decreasing or increasing towards the center. So the degeneracy rises considerably due to Pauli principle, and then these solutions have at the center a degenerate core, a highly degenerate core, which depend on the particle mass. So interestingly, it can be demonstrated that for degeneracies lower than 10, the thermal de Broglie wavelength in the core is larger than in the particle mean distance. That's why one calls this quantum condition, so-called quantum condition. And as I told you, the compactness of the core and therefore the wall profile depend on the particle mass. This is a mathematical solution, which I will show the phenomenology in a few slides. But let me go briefly to the thermodynamics of this theory, because one thing is to show the equilibrium solutions, but one would like as well to find the stability of the profiles. Therefore, to find dynamically and thermodynamically stable configurations, one needs to solve the second order variation problem in entropy in general relativity, which is quite complicated if one would like to solve numerically, analytically, because the equation of a state in this problem, as you recall, is not polytropic. It's not barotropic. It's so, and then, but importantly, there is a way to solve this problem, which was proposed by Katz. So sometimes called the Katz criterion, which relies on analyze all the sequence of equilibrium solution along a caloric curve, and study the derivatives of this caloric curve. And so one has to build this caloric curve of energy of the system versus inverse of temperature of the system. And therefore, we have done this for the first time in 2021 for realistic masses of halos, or order of 10 to the 10, because previously this has been done only for toy models by Chavani. So the caloric curves you obtain out of this form. So this probably recalls some of you of the so-called gravothermal catastrophe, which correspond to the total energy versus inverse of temperature, which in the case of Boltzmann's distribution, this goes to a spiral when the gravothermal catastrophe sets in. But in the case of fermions, the fermions halt here. The spiral is not go to a spiral, so it derolls and go this trend. And so in blue, this caloric curve correspond to the stable solutions, while in dotted are the unstable. So between this inner spiral, which is here very, very small here, but very compressed, when this is rolling, these are all core halo solutions which are unstable, but then enters an interesting stable regime. And an important point is this point C, which is the last stable configuration, which can be formally demonstrated to be the last stable configuration of the system. And I will show in the next slide the profiles you get out of this solution. So this framework can be linked to cosmology in the sense that for this particle mass, I'm telling you, for example, order 10 keV, which is preferable for these models. You can solve the power spectrum using class, for example. Then you can apply the extended projector formalism and find the corresponding virial, the typical mass corresponding to the virial radius of the halo. And then you choose, for example, let's say for Fourier curve, for this case of the purple line, you have this mass, typically collapse halo, and then impose this as a boundary condition to make this caloric curve, meaning to resolve all the equilibrium solution with this particle, with this halo mass, and you find, for example, these are three typical solutions for given energy, 1, 2, and 3, which corresponds to this solution here, 1, 2, and 3 for a given energy in the caloric curve. So the upper one is a diluted Fermi profile, resembling a pseudo-thermal sphere. But then, due to the transition here to the quantum regime, you have two more solutions, two core halo solutions, 2 and 3, which one is unstable, but the other is thermodynamically and dynamically stable here, 3. So this solution corresponds to this core halo profile I'm showing. And as I will show in a few slides, the interesting part is that this halo part can be shown to be astrophysical, meaning to explain rotation curves, while this highly degenerate core can mimic the effects of a supermassive black hole, but not yet collapsed. So regular solution, but all in terms of dark matter. So, yes. So this example was of 50 Kev. So important is that, as I told you, this point C, the last stable solution, can be further demonstrated to be really the point of collapse, where you have core collapse to a supermassive black hole using the turning point criterion, which is has been developed. Well, this comes from I would say even the 70s or so, but the world has put more in last decade, in 2014, that put more general theories about turning point instabilities. And for cases where your equation of state is so when you can follow a monoparametric family of equilibrium solution along this total mass versus central density, the maximum is the turning point, and so solutions to the right of this maximum necessarily are unstable, but to the left are not necessarily unstable or stable, this depending on the equation of state. And in our case, for this cell gravitating system at finite temperature, you find that the last stable configuration of the total halo corresponds to the minimum of this curve. It was an important result because never had been done for finite temperature. Rezzolla and colleagues made an analogous conclusion, but for rotating neutron stars. In this case, so they added these new degrees of freedom of rotation, but in this case, the new degrees of freedom is temperature. Of course, in this case, the application is to halos and not to neutron stars. Okay, so this, so phenomenology. So now this theory we have applied recently to 3 different virial masses from 10 to 10 up to 10 to 12. And you can see here the 3 caloric curves for a fixed particle mass of 100 keV. And you can see that there are 3 different solutions at the criticality. And here is the sum. And therefore, one can wonder if there exist solutions for these halo masses where the core is critical, so on the verge of collapse to a black hole and surrounded by a halo. And interestingly, the answer is yes, and this is the main statement of this talk, which it does exist solution to Einstein equation of spherical symmetry for cell gravitating neutral fermions, which gives hints to the mass of the dark matter particle, because for 100 keV, you have these core halo profiles, where the core becomes critical. In this case, the critical mass is a seed of 6 times 10 to the 7 solar masses, which is surrounded by a halo, which you can demonstrate that the halo, you follow all the equilibrium solution of the caloric curve, it ends up that this critical solution follows this is to show that the halos are astrophysical, meaning which fulfills with the dark matter surface density relation, meaning the relation between the plateau density with the one halo scale length, which follows the pioneering paper of here our colleague Paolo with Donato and Gentile in 2009. Very important correlation which any model of dark matter halo have to fulfill. And so we show that these halos fulfill with this condition while they have a critical core of collapse in general relativity, demonstrated by a collapse criterion in general relativity. So I think this is a very interesting result because it's showing that halos at violent relaxation can be, when accounting for Pauli principle, can develop these very dense cores which eventually can collapse, and therefore you can end up with a supermassive black hole made of dark matter surrounded by a halo which is of astrophysical nature. Okay, so we have this. I will go fast here because we have done the accretion. I don't know how much time I have, but we have done the accretion, the subsequent accretion. So we compute once this seed of is formed of the black hole, you have a accretion disk, and it starts to accrete matter and radiation in the most general case, and start to gain mass and angular momentum, so it becomes a kerr. And therefore, we have calculated, and this is the main result here, where in the first here you have the time from formation, time delta t. So in the first gigayear of the universe, for parameters of accretion which is below critical, so let's say below Eddington-like, so not hyper Eddington, you are always on below Eddington regime, you can grow your mass, your initial seed, which started at 10 to 7, you can end up, for example, in the first, for 0.4 gigayear, for example, you can end up in the order 10 to 9 solar masses. And this is important because it it provides heavier seeds than baryonic channels. And as I will show, that in the last few minutes, I would like to show very fast that if you don't want to use the critical solution, but eventually if the halo don't end up in this critical solution, but end up in a point of stable solution prior to critical, you can use for example, you can take all the data of the Milky Way, including the S stars, the central stars around Sagittarius A star, and you can wonder if it exists a solution of this gravitating system where the gravitational potential can answer for both kinematics, the S stars plus the rotation curve kinematics with the same profile. So you have to solve the boundary condition problem with specific values. And interestingly, it exists a family of this core halo solution, which I've shown before. For example, this is an example that you see here for a rotation curve on the right, where this is a logarithmic plot. That's why the core looks so large. Where you have in the halo region governed by dark matter, then in the intermediate region you have the bulge and the disk, of course dominated by baryons. But in the central region, this core is again this dark matter core can explain the average circular motion of the S stars without the black hole. And this is interesting because for the same particle mass, but different free parameters, you can have regular solutions which explain this overall rotation curve. And we have, with the facility, the largest computational facilities in Argentina, we have done Monte Carlo with S2 star for 100 keV and compute the orbital parameters of S2 with the below or sometimes few percent or below precision with respect to the Schwarzschild black hole. And here are the posteriors for 100 keV. So this is to show that when you want to reproduce the geodesics of this two, you can do excellently with this regular core. Okay, and then we have applied also to other galaxy types, but I think I don't have time now. If there are questions, I can answer. And yeah, I will leave with this last slide about different dark matter channels, where, as you probably know, you have the different channels of baryonic nature, which corresponds to the direct collapse black hole or other baryonic channels like population 3 stars or runaway collisions, which explain some of the intermediate seeds of supermassive black holes. And in this theory, we propose now we have a new channel for supermassive black hole formation in terms of the collapse of these dark matter cores. Thank you.